In this short summary presentation, I'm going to attempt to outline the work that was published in Applied Mathematical Modeling in a paper titled Discrete Boundary Smoothing Using Control Node Parameterization for Aerodynamic Shape Optimization. I'll try and do this in under 5 minutes. The work was primarily undertaken by a PhD student of mine, Dr. David Naumann, now Dr. David Naumann, and my name is Ben Evans. This work was done in collaboration with Sean Walton and Dubey Hassan, all from Swansea University. Essentially what we were doing in this work was trying to extend and improve on a method that we had previously published in Applied Mathematical Modeling back in 2011. In this work, we were attempting to develop a novel method for aerodynamic shape optimization based on computational fluid dynamics simulation results. So optimizing geometries for things like drag minimization or lift to drag ratio maximization. Now, we identified in this paper that one approach for doing this would be to use the node positions that are defined in a discretized version, a discretized description of your geometry used in computational fluid dynamics as the degrees of freedom in your problem. But of course, for a realistic complex geometry, if you used all of the nodes in your computational mesh, your discretized description of the geometry, you end up with a huge number of degrees of freedom. So we decided in this work that we would select a subset of those nodes that we would define as control nodes. The movement of these control nodes would be independent and driven by the optimizer. In all of the work in both papers, the optimizer was a gradient-free, a population-based evolutionary algorithm. And the movement of these control nodes would then define the movement of the rest of the boundary nodes defining the geometry. One of the shortcomings detailed in that 2015 paper of this method was that based on the kind of interpolation schemes we were using to move the boundary, what we would often introduce if you had large movements in those control nodes were discontinuities in the gradient, detailed here in the bottom figure, figure A. So discontinuities in the gradient, or kinks as we would refer to them. So in this paper we wanted to develop a scheme where you could smooth out those discontinuities that were introduced by large geometry movements. Essentially what we applied was a form of diffusion. We applied smoothing to the geometry as a post-processing step after the control nodes had been moved in a geometry transformation. This algorithm was developed and is detailed in the paper. We wanted it to be kind of geometry independent, we wanted it to be mesh resolution independent, and we wanted it to be something that could be controlled in principle by either the designer setting up the problem or by the optimizer itself. So how that was implemented is the first part of this paper. Geometrically, the first test problem that we wanted to explore was, could we drive an arbitrary starting shape, so in this case a circle, towards something that looked realistically like an aerofoil. Now in this problem, this is more challenging than you would think using this approach, because for the majority of this shape you want to maintain smoothness, you want to apply this smoothing parameter to any movements introduced by the control nodes. But of course you also want to be able to introduce a sharp trailing edge. You don't want to smooth out that trailing edge. So we managed to show that that was possible using this scheme. The next problem we looked at was just geometrically, could we drive a starting point aerofoil shape, in this case a NACA 0012, towards a known geometry. So independent of the kind of aerodynamics that are going on, if the fitness function, which is what was driving the optimizer, was just simply the difference between those two geometries, could you drive one to the other? And how did the optimizer behave with different numbers of control nodes and different positionings of these control nodes? So that is the second study detailed in the paper. Aerodynamically, the first problem that we attempted to solve was inverse design of an aerofoil shape. So in this case we started with the NACA 0012 aerofoil geometry, and we wanted to drive that shape towards a known pressure distribution, a pressure distribution that we'd already run based on an RAE aerofoil at a transonic Mach number where you've got a standing shock wave on the surface. Aerodynamically a very sensitive problem. the aerodynamic response of that aerofoil is very sensitive to geometry movements, and we were able to show that this scheme was able to solve that problem. And finally, we applied this approach to the design of an intake duct, an aerodynamic intake duct delivering air to a hypothetical jet engine. And we looked at how you would do that in terms of maximizing the pressure recovery delivered by the intake and also the flow quality at the engine inlet, and how the optimum intake duct design varied between subsonic and supersonic flow conditions. All the details are available in this paper published in 2017 in Applied Mathematical Modelling. If you have any questions or want to know more about that paper, please don't hesitate to get in touch either via email or via Twitter.